Laura. Nous allons commencer par une présentation des membres du jury. Je vais leur demander de se présenter eux-mêmes et de présenter le rôle du jury. Donc, si vous voulez vous lever, vous vous tournez vers la salle des...
I cannot understand.
Oh, yes, yeah, the impact will happen in English, don't worry. So I'm asking the members of the jury to stand up and present, introduce themselves to the audience and explain the role of the defense. Yes. Okay.
I'm Vasil Hadjianu. I work in Vienna, the University of Music and Performing Arts in Vienna, the Department of Acoustics. And my role here is the rapporteur, if I can pronounce it correctly. So I have already read the thesis, written a report, and I might have some questions.
Je suis enseignant-chercheur à l'Université de Chrétienne et la spécialité c'est la physique et la vibration.
Bonjour à tous, je suis Thesis, je suis violoniste professionnelle et aussi chercheuse, mais pas du tout dans le champ de l'acoustique, avec plutôt des recherches autour de l'interprétation en tant que violoniste. Et c'est bien à ce titre qu'on va solliciter pour ce jury.
Bonjour à tous, je suis Frédéric Delgacois, je suis directeur de recherche à l'UQAM, de recherche qui s'appelle UMR SCMS entre Sorbonne Université, CNRS et l'UQAM. Et moi, je suis spécialiste de l'interaction entre mouvement et vision.
Bonjour à toutes et à tous, moi je m'appelle Vincent Keul, je suis maître de conférence à l'Université de Bretagne occidentale à Brest. Ma spécialité à moi, c'est plutôt la perception sonore. Je suis examinateur de cette thèse et je suis aussi un violoniste amateur.
Je suis professeur à la faculté de musique de l'Université de Montréal. Mon champ de recherche, c'est la musique musicale, et en particulier le talent instrumental et le rapport entre le geste et le son instrumental.
Merci. Je m'appelle Julio Spaletta et j'ai fait HTT à Nantes. Et mon rôle ici, c'est surtout, comme je viens de l'Argentine, c'est de traduire en espagnol pour la famille de Víctor.
Bonjour à toutes et à tous, je suis Claudia Fritz, je suis chercheuse CNRS ici à d'Alembert et je suis directrice de cette thèse.
Bonjour, je suis Jean-Pierre Barthélémy, professeur à Sorbonne Université dans l'UFR de musicologie. Donc, moi, j'ai intervenu au tout début en tant que co-directeur pour une petite orientation musicologique de départ, parce que, comme vous avez pu le remarquer, cette thèse concerne principalement l'acoustique et qui n'est absolument pas mon domaine. Et donc, Claudia est évidemment là pour diriger cette thèse, et moi j'ai été là pour encourager, dire des mots gentils auprès de Víctor.
Bonjour à toutes et tous. Donc, Frédéric Ablitzer, je suis enseignant-chercheur à l'Université du Mans. Donc j'étais co-encadrant de cette thèse, voilà, avec une spécialité acoustique et vibration.
Merci beaucoup. Donc, nous allons passer à la présentation du projet de Víctor Salvador CASTRILLO. Donc, on vous donne la parole, vous avez 45 minutes.
Thank you very much. S'il y a des questions, vous pouvez me poser en français. So, okay. Thank you very much for being here. I'm going to present my thesis on the influence of violin ball mechanical properties on the perception and performance of violinists. It's a PhD that I did here in d'Alembert, financed by Collegio Musicae, and my thesis directors were Claudia Fritz, Jean-Pierre Bartoli, and Frédéric Ablitzer. So let me first start with the main object of my thesis, which is the bow. Here I have one. and the bow has two main properties. I am focusing on modern bows, which have been assembled since the end of the 19th century. 18th century, sorry. So there are two main parts, which are the hair of the bow that comes in contact with the string, and the stick of the bow, which has the main function of keeping the bow hair under tension. In this thesis, we have focused on two main mechanical properties. First, we focused on the flexural rigidity to see if there was an effect on the perception and the performance of the musicians. And our main focus has been on the mass distribution of the bow. So this is how playing violin looks like. Very schematically, the violinist is going to, here a violin, interact with his or her instrument with his or her two hands. So we have the left hand that pulls in the string, and it controls the length of the string, controlling the pitch of the music or the sound that will come out. And then there is the sound production mechanism, which is made through the bow, if not through pickato or by plucking the strings, but generally we come bowing the strings with this element. So the two main sources of perception during this process are the violin and its sound itself, and also the vibratory response that may have, and even bone transmission. But our main focus here is not the left hand, is the bow. How the violinist interacts with this element, and how he perceives its quality through haptic sensation, and also through the sound of the violin made by the bow. There have been several investigations in this scope, in this process, since the late 20th century. There's been aspects we got interested in measuring the both control parameters of violin performance. There have also been many theses on the movement of the capture of bowing gestures, but also in the biomechanical effects of the bow on the musician itself. And most lately, with the thesis of Timothy Wofford on the playability of the cello, and most recently, this year, where there have been research on the reproducing bow kinematics on the cello, but with a robot. Regarding the bowing mechanism and the production of sound, there have been research concerning the mechanics of the bow string. What are the main bowing parameters that determine the vibration of the string? And there have been also research regarding the bow and how the bow influences the sound production. Concerning the perception, there have been also research on how the bow is perceived and which on some mechanical properties, for example, the damping, modal damping, and just the perception of different bows, and analyzing the vocabulary that is used for describing these bows. Those are some of the studies that have specifically focused on changing properties of the bows and how they interact with the string or with the perception of the musician. I cannot forget work by Ablitzer and Camber of the bow and the hair tension, or Goff regarding the bow vibrations in contact with the string. So this is our field, and we have studied this interaction in 3 experimental studies, with all of them involving musicians. The first one is a preliminary study on the pre-humbuck transients produced with different cello bows. Then we did a study on the perception of different bow mass distribution, and finally we investigated the influence of a specific property given by mass distribution, which is the moment of inertia, on the bowing parameters of a certain technique of violin playing, which are the bouncing strokes. Those strokes are like spiccato, sautillé, that require the bouncing of the bow on the string. So let me first start with the first one and explain how the sound production process works. So When we bow a string, the bow comes in contact with the string, and through a friction interaction, it excites the string, which in turn self-vibrates, self-oscillates, and this vibration is transmitted to the sound box through the bridge, which in turn then acoustic radiation occurs, and we get to hear the sound of the instrument in our ears. By measuring the excitation of the string on the bridge, we get to measure one of the first sources of sound of the instrument. And that's what we will be doing to measure things like this. This is the most expected periodic solution of the bowed string, and it's called the Helmholtz motion because it was discovered at the end of the 19th century by Helmholtz. And it describes what the string, how the string behaves under the friction of the bow. It's a two-phase mechanical dynamical behavior, and these two phases are the sticking of the string to the bow, and the slipping of the bridge of the string under the bow. So this is stick, then it slips, then it slips. And this excitation, this vibration, periodic vibration, generates a force in the bridge that has this sawtooth form, on which, for example, with two faces, if you see the big sticks on the force, those are the faces of the slipping, the string under the bow, and the more slower slopes are the sticking faces. This mechanical behavior, this behavior of the string is determined by the bowing parameters, which are for both the sustaining of the Helmholtz motion and the triggering of this kind of vibration. First one is the bow velocity, which, for example, determines the amplitude of the waveform. And there is also the hair bridge distance and the bow pulse on the string. And before the creation of this Helmholtz motion, depending on the bowing parameters, we can get what is called a pre-Helmholtz transient, which can sound somewhat creaky at the beginning of the sound. And it is something that normally the violinists are trained to avoid these kind of harsh attacks and unwanted sounds at the beginning of the notes. So this is our focus, specifically the pre-Helmholtz transient, and we want to see if the different bows produce different pre-Helmholtz transient. Gettler simulated the conditions for the creation of length of transient, pre-Helmholtz transient of a specific length. This is a phenomenological diagram, but you can see that there is a region in the control parameter space with which we can obtain what is called as perfect transients or shorter transients. That is, we can get to have the Helmholtz motion much quicker than with other conditions. And this, as I was saying, depend on the force on the bow, the acceleration, but also on the hair bridge distance, which is not represented here. This diagram will be just for a fixed hair bridge distance. So we see that there is a dependence on the bowing parameters of the transient length of the pre-Helmholtz transient. And now we wonder what are the mechanical properties of the bow that could have an effect on this pre-Helmholtz transient. So we can have bows with different elasticity. We can have stiffer bows or more elastic bows. And if we analyze the gesture of the musician when he presses the string with the bow, a stiffer bow, for example, if we want to make exactly the same force, we would need to rotate our hand more if we have a more elastic bow than if it is a stiffer bow. In other words, for the same rotation of the hand, we will have a larger force on the string than if we are performing exactly the same rotation with a softer bow. As we know that this force on the string is a control parameter that determines or influences the length of the transient, we wonder if musicians are, when performed, the transients are performed by musicians, do they produce different transient lengths with bows with contrasting stiffness? And we wanted to verify this by using different bows with different players. So we used an instrumented cello, which has these piezoelectric sensors between the grids and the strings, and we get to measure this force on the bridge. So we used this cello and different bows with contrasting stiffnesses. We invited two professional cello players to produce a set of attacks on the bow at different places, at different dynamics in piano and forte, piano being less loud and forte being louder, and at two parts of the bow to see if, for example, when we perform the attacks at the tip, the effect of the bow mechanical properties will be larger than if we are performing the attacks here, because here the control is more direct between the violinist and the string than here. Here, the mechanical properties of the bow would have a greater influence on this, on the control of these parameters. And finally, we asked them to simply give us their opinion about these bows as if they were in a purchasing process, if they wanted to buy a bow. To do so, we recorded all these signals and we explored different methods. The first one, we did not use this Galuzzo's method, which was proposed by Galuzzo in his thesis, because it requires the bowing to measure the bowing parameters in order to perform. But we explored different techniques, like the ratio between different frequency bands of the signal with a short Fourier transform function, and other methods like the distance to an ideal sawtooth waveform to detect the onset of the Helmholtz regime, which will be the end of the transient regime. But we finally chose to use a method based on the periodicity of the splitting phases that we can discuss afterwards if you want. Finally, we analyzed all this data and we did not find any significant effect of the bowing, of the stiffness of the bow with the performed transient lengths. What we see also is that, for example, at the prop, where the interaction between the musician and the string is less important, is more direct. We see that there are differences between musicians. For example, musician 1 in forte, which is here represented in quarto, plays shorter transients than musician 2, but in piano, the inverse occurs. Musician 1 plays longer transients in bows A and B, which are the bows that are common to both musicians, than the musician 2. And actually, there have been attempts to measure, experimentally measure the transient lengths. For example, Lampis this year published a set of transient lengths depending on different control parameters, and we see that even in this playability, what they call playable region, which will be the region where the transient lengths are shorter, we see that there are bowing parameter conditions that generate transients that are longer than just varying a little bit. We see that we have black spots of more than 20 periods next to perfect transients with 0 periods. This makes this tell us is that there are some chaotic behavior of the string under these conditions, and we can have transients of varying lengths with little changes of the bowing parameters. But we also asked them to give their opinion about the bows, and they both of them chose the bow B as the most prepared one because of reasons like the comfort or the balanced weight distribution. We thought that this weight distribution could be linked to the mass distribution of the bow itself, so that's the reason why we chose to start a new research, a new study. on the perception of violin bow mass distribution. In this case, we won't be focusing on performance, but we will be focusing just on the perception. So our hypothesis on this study was that the center of mass position could be perceived differently depending on the weight perception. That's it. The closer the center of mass to the frog, the lighter the bow it will be perceived. Why? Because when we approach the center of mass to the frog, the effort made by the little finger will be less effort to keep the rotational equilibrium of the bow. And then when playing, there will be differences also in the necessary finger forces to exert a specific force on the string. So if we want to make the same force and the center of mass moves, the equilibrium between the index finger force and the little finger force, which are the forces that govern this kind of motion of the bow, would be different. And on the other side, the moment of inertia, which is the equivalent of mass in rotation, that is, the higher the moment of inertia an object has, the harder it will be to rotate. So the higher the moment of inertia, the higher the effort will be to shake it or to simply do this kind of motion. So it should be perceived as louder, as heavier than a bow with less moment of inertia. And when playing, not only this kind of behavior could be perceived like for a heightened, with a heightened weight of the bow, but there is also the frequency of the natural frequency of the bow in contact with the string that is lower when the moment of inertia is higher. So the higher the moment of inertia, the less quick it oscillates when in contact with the string. In order to investigate this, we asked a bow maker to build a bow, and it was Julius Paleta who gently collaborated with us by creating this Pernambuco bow that I am showing here today, and that has the particularity that is very light. It's 7.5 grams lighter than the standard, and it allows stick magnets to change the mass distribution and reach the total mass of 60 grams, which will be perceived as a standard, or at least considered as standard in the bowing community. At least for violin, modern violin. Magnets were covered because we will give this bow to the people so that they can tell us what they perceive. They will be covered so that they can perceive visually the changes that we are making to the bow. What this bow allows is to change specifically one specific property. If we change from one bow to another, there are a lot of parameters that may be changing. For example, the amount of hair, the tension of the hair sometimes, it is not exactly the same. The elasticity, there are multiple parameters that are changing from one bow to another, and it is very difficult to isolate the effect of one property if it is changing with other properties. So what this bow allowed us is to specifically focus on the bow mass distribution to determine if this property is well perceived or how it is perceived. So the two main parameters that are given by mass distribution would be the center of mass or center of gravity and the moment of inertia, which we can measure by hanging the bow from the rotation from an axis that is placed in here, because this is where normally the violinist will put the thumb, and it is around this axis that the bow pivots, and we can make a physical pendulum of it and extract the moment of inertia around this axis from the frequency that we observed. We designed 5 mass distributions with Amelipika, and all of these distributions have the same mass, which we wanted to keep it the same to see if both the moment of inertia and the center of mass could produce were perceived and how they were perceived. So this distributions are considered as within the normal limits of the bow mechanical properties, because we measured a set of 14 bows to see if these sets of mass distribution fall within the normal values. And there are two outliers on one specific parameter, bow E, that is an outlier in the center of mass position, and bow C, that is an outlier in the moment of inertia. So in order to investigate how these properties are perceived, we perform, before knowing how they are perceived, we must ensure that they are perceived indeed. So we performed a discrimination test to verify if the musicians could detect small or large changes, and a free evaluation test to analyze how they describe these changes. So we used concepts from signal detection theory, which states that decision-making occurs amid some level of uncertainty. So imagine you have two stimuli, acoustical stimuli, one with noise and one with signal plus noise. The one with noise will follow a normal distribution, in the sense that sometimes we'll perceive this stimulus here, most probably here, but sometimes it could fall here, or it could fall here. And the same for the signal and noise stimulus. If we ask the person to say if there is signal in this stimulus, if the time we present this signal falls above a given criterion, they will say yes, there is signal. But if that time the stimulus is perceived below this criterion, they would say no, there is no signal. So there's always this kind of uncertainty in the decision-making process of the discrimination tests. So we used the difference between two stimuli is called in the domain D prime, and we tried to calculate the D prime of our bows, and in this time the input, what we are changing is the mass distribution, the parameter that we are focusing. So we performed two tests in different conditions. We performed a holding and shaping the bow in the air test. That is, we asked them to evaluate if the bow was changing by just keeping it horizontal or gently shaping, and asking them which of the bow of the series that we presented, with always the reference in the middle, was equal to the reference. And similarly, we performed a playing test on which the reference was presented twice, because it was in previous tests that we did, we thought that it would be better for the musician with a less cognitive charge for him or her to evaluate the differences between the bows by presenting the reference twice. We also asked them how sure they felt about their response, and all this data will be used for the calculation of D prime. Again, we can talk after about the process of how these D prime values were obtained. So this is the results from both tests, and we see that in the first test, where the violinists were asked to say if both the stimulus are, if they could detect these changes, we see that the stimulus with higher change in the center of mass position was perceived as different, and that the others we cannot conclude actually if they are perceived different or not, mainly because of little number of participants. But and in the second discrimination test, we saw that in turn what was perceived as different more was the changes in the moment of inertia, both in little and big amount of change, in both little changes and higher changes. Finally, we performed this pre-evaluation test as we did before with the cello bows, but with the bows with changing bow mass distribution. So we asked them to describe the differences between the reference bow and the bow with higher change in moment of inertia or with higher change in the center of mass position. And we analyzed all their comments and categorized their comments into 4 main categories. Which are comments referring to a spiccato change, a change in bouncing stroke like spiccato, change in heaviness, change in playability, or other changes that could go, for example, about the sound quality of the bow. We see that in the case of a bigger change in moment of inertia, the amount of comments on a change in the behavior of the spiccato of bouncing strokes, on spiccato, was higher than in a change of the center of mass position. And specifically, 6 participants talked about the displacement of the bowing point towards the tip when we increased the moment of inertia. And then concerning the weight perception, we categorized all the comments that referred to a change in heaviness, and we saw that even if all bow mass distributions here have the same mass, we have that a higher moment of inertia is indeed perceived as a heavier bow, and a moment closer, center of mass closer to the frog is perceived as lighter. They also gave comments about different parts of the bow, but here I represent only the totals. So in conclusion, violinists did not seem to perceive a little variation in the center of mass, but they did detect a big variation when they were holding the bow in the air. And in turn, when playing, they did not seem to perceive changes in bow in the center of mass position, but they did perceive changes in the moment of inertia. This would, well, also concerning the changes in the perceived weight, we saw that even if the weight was the same, changes in the bow mass distribution were perceived as changes in the weight perceived weight. So the change in behavior of the moment of inertia of the bow under change in moment of inertia was perceived as a change of behavior of the bow when performing bouncing strokes, which would inspire the third and last study on the influence of bow moment of inertia on the bowing parameters of bouncing strokes. So as I was saying, they perceive this change, and we wonder if we fix this bouncing ring, can we measure this displacement, and if there are maybe other effects that we are not they perceive, but they are there other effects on the way the violinist uses the bow when playing bouncing strokes. So to do so, we used motion capture technology, on which we placed little reflective markers in the bow, for example, here or here, in order to, in the violin and in the bow, sorry, in order to track the position and calculate the main bowing parameters that are used during playing. These parameters are the 6 degrees of freedom of the bow, which are 3 distances and 3 angles. The distances are the distance from the frog to the bowing point and from the fritz to the bowing point, but also the distance between the hair and the string itself. And the 3 angles that are rotations around the 3 axes defined by the distances. And they are called the tilt, which controls the amount of hair that is in the string, the inclination to change from one string to another, and the skewness, which is the angle of perpendicularity of the bow on the string. So we did 2 tests. The first one was a technical test on which we asked the performers to find the sautiller point of the bow. This point is defined as the point where the bow bounces naturally, and we asked them to always start in a specific position of the bow and move at a given rhythm to found where the bow bounces naturally. So we asked them to do this for at least 5 seconds, and with the bows with contrasting moment of inertia, and in different situations. For example, changing dynamics and also changing the strings. One in the G string, which is the lowest pitch string of the violin and the A string. So here's this, a representation of this test, which we call technical test. Which I have shown you, so it's okay. You I have already. Oh. No worry, I can show you after. And then we asked them to perform the a musical test, on which we invited them to perform a well-known excerpt, which is the introduction to Mozart Magic Street, which has multiple quavers in pizzicato, and we asked them to do it in also with both with contrasting moment of inertia and in dynamics to see if there were changes in the bowing parameters due to the bow. So this is the excerpt, and it should sound like. So that is the orchestra part. That will be the solo violin, first violin part. We have, as I was saying, a lot of bouncing strokes, and we focus specifically on two parts, which are identical bars, but with contrasting dynamics. The first one in piano, and the second one. So we have the musical material to come analyze how the bouncing behavior of the bow is affected by its moment of inertia. So we invited 16 participants, and we calculated in these two tests the average bowing parameters. For example, in the Southier point, where they had to find this bouncing point of the bow and keep it for 5 minutes. We calculated the average over the 3 minutes, 5 seconds, the 3 last seconds. And these are the results. And we already see differences, not only in the parameters, but also the musicians are grouped by colors. And we see that they are most of them are consistent with themselves in where they play this, they find this bouncing point. So it seems that it's not only a bouncing point that is given by the bow, but also by the musician. Okay, so we have all this data, and similarly in the Mozart Pizzicato, we specifically analyzed these 4 quavers of the excerpt and calculated the average bowing parameters, which led us to have a lot of data and we see that from one musician to the other, the average bowing parameters change not consistently. They are consistent with themselves, but they change from one musician to the other. So we fitted some linear models, but with the particularity that were linear models that take into account the musician as a random effect. For the technical test, as we have 3 factors that were changing, we have 3 effects that we consider as fixed effects, and the coefficients of this regression will be the coefficients of corresponding to each effect. If these coefficients are significantly different from 0, that means that this effect has the bow or the dynamics have an effect on this parameter when we change it. And we did similarly for the musical test, but this time with 2 factors because the string was always the same. And as a result, we obtained, here I represent only the bowing parameters on which we observed significant changes due to the bow. We have the technical test. We see that there is a change, but it's a slight change, significant, but still very close to significance, to the 0 threshold. And we see that this effect, although it is significant, it is much less important than other effects, for example, the string on which we are playing or the dynamics we are using. In other words, for example, for the position of the bouncing point on this bowing parameter, we see that the bow, when we increase the moment of inertia of the bouncing point shifts toward the tip, but it's also the case, and by a much more it is a bigger effect if we change the dynamics from forte to piano. So in conclusion, in this thesis, we have worked on this on the violin playing process and focused on performance and perception. At the beginning, we tried to see if the bow had an effect on the produced pre-hand hook transient lengths, and calculated in a preliminary study with 2 musicians the lengths of transients performed at different with different under different conditions. And we also asked them what they perceived as different. They both had the preference for the softer bow, and they gave results that were apparently far from changes in the flexibility of the bow, and maybe more in relation with the bow distribution, because they felt more even weight distribution of this softer bow. Then we focused specifically on this bow mass distribution, and we performed discrimination tests to measure to what extent participants were able to differentiate bows of contrasting mass distributions with 2 tests: the holding test, on which the bow with lower the center of mass lower closer to the frog was perceived as most different, and also in this playing discrimination test, in which the bows with contrasting moment of inertia were perceived as different too. And we asked them also to give their opinion on the bows that were most different in these 2 parameters, both the center of mass and the moment of inertia. And at the end, following the fact that some of these participants evoked a change in the bowing parameters when they were playing bouncing strokes, and specifically with the changes in moment of inertia, we performed this latest study only considering changes in moment of inertia, and discovered that there were significant effects of the bow on the bowing parameters that match what the participants of the previous test were saying. That is, that the bow shifts towards the tip when the bow increases its moment of inertia. But these effects are lower than when we change other factors. For example, when we perform the same excerpt in piano or in forte. And as a perspective, we would like to extend the analysis of transients, because in this study we have just focused on transients on the open A string, and we would like to move forward and consider other strings, but also other situations and bowing situations. And to do so, we should optimize our transient detection algorithm, because it has been optimized by hand for the case of open A string excitations. And with the latest research on this, we think that we can improve our algorithm thanks to the publication of a dataset of well-levelized transients. That is a lot of transients that we can come with our algorithm and compare the results of our algorithm with the results that were published. And the second one will be a bunch of signals that we recorded, but we have not used yet. It is we placed this pickup on the bridge, in the bridge of the instrument, at the same time that we were recording the excitation of the string. Why we did so? Because we have we would like to from this excitation and without using this kind of quite complex measurement equipment, be able to measure for example, the length of the transients. And if we compare the transients detected from the piezo signals to the signal recorded with this piezo, it would allow, for example, to put the piezo and not use this kind of instrumented bridge and obtain the excitation of the string from this kind of signals from other instruments that are not kept instruments that we keep in the lab, but are just the instruments owned by the musicians. Finally, we like to use perceptually classified bows. That is, bows that are not only different, but different in some specific ways. For example, some of the musicians and bow makers evoke the facility of some bows to produce consonant-like sounds or attacks. For example, more direct or sounds or more sounds that, and it is a specific perceptual category that we would like to investigate. But to do so, we need a lot of bows and a pre-classification of these bows by the musicians. Another perspective that we would like to investigate is the relationship between the perception of the bows, that is how the bows are perceived differently, and how the violin sounds in capturing the bowing parameters in the same time, in order to see if the differences that violin players and cello players perceive are some way correlated with this other kind of data. To do so, we where there is an instrument violin bridge that will be used with the motion capture, and in this way we will have all this data that will help to obtain these further clarifications on how the bows are perceived and why they are perceived as different. And finally, there is obviously other mechanical properties apart from the bow mass distribution that could be analyzed, and the influence of these variations not only in the mechanics of the bow itself, in how the bow behaves on the violin, but also how the violinist perceives it. That's it. How differences in the biomechanical level occur when we perceive a bow as more as softer, for example, or as more rigid or louder, for example, than another bows. Thank you very much.
Victor, for this very good presentation. So we are going to start with the comments and questions of the two external examiners, the rapporteur, Vassilios Chatsilia, sorry, and Nicolas Daucher.